Welcome to the afternoon session. I have the privilege to be the moderator for the lightning talks. My name is Kristen Koska, and I work at IQVIA with Christian. And I am delighted to have our speakers this afternoon. So if you are unfamiliar with lightning talks, or if this phrase doesn't translate, it's going to be rapid presentations. They have 10 minutes, nothing else, 10 minutes, and they will be shown off stage. And they actually all have posters that you can find them during the collaborator session. And so this is going to be quite interesting. As we mentioned, they have been purposely structured in a way that it will go along that continuum. And our first speaker is Alex Davidov. He is a medical specialist with OHDSI. He is going to tell us a little bit more about standardization of European medical vocabulary. So he is in the weeds. He's really doing some cool stuff. So he's got 10 minutes to impress you, and later he'll tell you more about his poster, but welcome, Alex.
Hello, everyone. I'm Alex Davidov from OHDSI Data Services Company, and I'm here to present to you the study performed by the OHDSI vocabulary team. Thank you for the opportunity of being here and sharing our results. Unfortunately, not all the involved folks are able to attend the symposium, but at least you can meet our mentor, Christian Reich. Currently, OHDSI is mostly based on the United States terminology. The Eden project has started, but it's not the only member from Europe. We are in touch in numerous of autonomous institutions in Europe, which are already connected to the OHDSI network. That's why we at the OHDSI community should be prepared to fulfill the growing needs of OMOP European terminology. We took a look at the landscape of the European vocabularies used. That's what we found. Look at the various European countries and the list of vocabularies used. Don't read the fine print, just get a general feeling where we are in Europe. We clustered the list by the SIDIAP domain and by the degree of the current vocabulary coverage by the OMOP CDM. Is it OMOP completely or just partially? Is it familiar vocabulary or obscure one? And some more granular variants. We have no purpose of running through the countries during this short talk, but please visit our poster later during this day. As you are probably not surprised, the overall quality of the vocabulary resources is poor. Even the detailed browsing of the official web pages of responsible committees not always make a success. From time to time, we have to dive deeper, finding the data in some unexpected places. We found a set of vocabularies being widely used. In general, they're represented by two different types: linguistic variants and national modifications. Linguistic variants are just the translations to the national languages without any semantic modifications. Once an international version of such vocabulary is implemented, all the national versions may be processed automatically, with the local names being stored like the concept synonyms. And these vocabularies are the United States clinical modifications of ICD-9 and ICD-10, and the vocabularies being widely used in the majority of the countries: ATC for medications, LOINC for lab tests, and ACD-03 for oncology coding. The national modifications or extensions, they use the original vocabulary like a basis with the application of the number of adjustments or alterations. That is the ICD-10 and SNOMED. ICD-10 is the best example of nationally modified vocabulary and used in most of the countries. Here you can see what we currently have. In green is the number of codes from the original version of ICD-10. Blue are the codes we can carefully take from the United States version of ICD. And orange is what is missing. On this slide, you can see the German, Polish, and Spanish modifications are very similar to the original version of ICD-10. Conversely, Czech, Dutch, and Swedish versions have a lot of new codes. By the way, United Kingdom and Italy simply use the original WHO edition of ICD-10. On the previous slide, I showed you what exists, and that's what is mapped. We already have some of the European datasets are OMOP, so the utilized vocabularies are OMOP as well. Some of these vocabularies are fully integrated with mappings and regular updates, and some of them have just partial integration. Here we can conclude that MEDRA, AMIS, and BDPM vocabularies need to be updated to be completely mapped. The next thing is heterogeneity in coverage among domains. Some domains are covered better, some not. The measurement domain is the most covered. The condition domain will be covered enough after we process several international vocabularies and some national modifications. In drug, we can easily deal with ATC on the higher level, but to cover the product level, we have to process a lot of national vocabularies. Procedures is the most heterogeneous group and still needs to be done. By the way, our new mapping algorithm based on the procedure attributes may be applied as well. You can actually find an original poster beyond this room to learn this algorithm in detail. And finally, the new challenges. We have a lot of things to do, like ICD-11 implementation, and a list of national vocabularies and national modification needs to be done. But first of all, we should prepare the development plan to meet the stakeholders' needs and to cover the top priority areas. Otherwise, we are at a risk to be drowned in dozens of new vocabularies and millions of concepts. Okay, let's summarize. Although a lot of work has already been done, the European medical vocabularies are not covered completely. And here we can easily find a great bulk of work needs to be done. But having a large variety of methods, tools, and practical experience, the OHDSI vocabulary team is ready to take this challenge and start the European vocabulary incorporation. So we will prepare comprehensive and sequential development plan, so stay tuned. Thanks. We have no questions, right?
You're good. Thank you, Alex. He might get the record so far for most on time. Our next speaker is Fatima Alnova. She is a health informatics research specialist in Saudi Arabia. She works with the Saudi Food and Drug Authority, and she's going to talk to us about the conversion of Saudi Arabia electronic health records using the OMOP Common Data Model. Welcome, Fatima.
Hi, so before I start, I just want to ask a question. Who here is relatively new to the OHDSI community? Just raise your hand. Amazing. So before I start, I just want to say that we are here, same journey as you. We've begun this journey about 4 months ago. And the main reason I'm here is to send the message and showcase how this journey is made and just to give you an enlightening experience about our amazing journey. I'd like to thank our collaborators, the 2 hospitals that have worked with us, Kingdom Hospital and Sultan bin Abdulaziz, and a special thank you to Claire Blacketer from Janssen Research and Development. Thank you, Claire. She's been actually my second hand, helping all of the team through the process. And thank you to the Saudi Food and Drug Authority also for their support. So just a quick background to give you about the project that we're working on. We're working on the pharmacoepidemiology database project. So its scope is to establish a representative national database to enable the SFDA authority to evaluate and identify, report any health-related effects to drug outcomes. The objective is to examine drug utilization, evaluate the safety and effectiveness, provide a descriptive summary, and to protect the health and well-being of the Saudi community. So here's the good part for all your newbies. I'm going to showcase now the method that we've taken. So it's quite not that similar to the methods taken from other OMOP communities. We are currently working on a pilot with one hospital that contains 85,000 unique health records. It's the first initiative in the Middle East to adopt the OMOP. And that being said, we have faced certain challenges that's unique. I could say it's unique to other collaborators. So, sorry, let me go back just one. So this learning curve, it resulted in us making it to 2 phases. First phase of adoption, and then continuing on to the second phase. And I'll explain how these phases will go on. So the first phase that we started this OMOP journey is that as a team, we sat down like in one table extensively for about like a month to understand the OHDSI concept. We went table, and the field that it had, what's behind it, how are these tables going to serve our scope, our pharmacoepidemiology database, what we need, what data do we need from hospitals, what experience do we need to allocate for us to build this OMOP database. So just a screenshot of our tables and scribbles here and there, what we need, what is required, what is not required to serve our scope. So now that we understood the OHDSI as a team, we started, okay, so we know what the tables are, we are aware of the mission, we know what, as a team, we started, okay, how are we gonna start this? We started with establishing the database. So we are using Postgres database. And the figure that you see here is, I'll just go the hospitals and this SFDA central database. I'll name it as phase 1. And then phase 2 will be the SFDA central database, that's the CDM. So during phase 1, what will happen is we will extract data from hospitals and then ETL that to the central database. And then after that, we would go and ETL again onto the CDM. So that being said, what are the challenges that we're faced? We have, So we have worked, when we established the database, we were like, okay, the database is set, we know our OHDSI mission, what is next? We need data to feed that database, to start working on the OMOPing the CDM. We met with hospitals, we explained our concept, our project. We started to convince them to collaborate with us in order to serve the mission and to spread out the OHDSI community. Successfully, we now have signed an agreement with 2 hospitals, public and a private hospital, and we are piloting on one public hospital. So the challenges that faced after receiving the first batch of data was lack of hospital awareness. You might say, why do you mean by lack of hospital awareness? You already met them, we described the mission that we have, but they didn't quite get the concept that we were trying to serve. Hospitals said, oh, okay, you want data? I'll give you data. They just send us about 85,000 and go, here you go. When we started to see an in-depth look into that data, there's like, okay, that's only descriptive English information. It was just diagnosis. There was no source codes, nothing. Okay, so what should we do? Go back to the hospital again. We need to enlighten them more on what is how is it their data that's going to help us OMOPing the database. So we requested source codes. So we don't just need English diagnosis, we need source codes that you had. So when we went to the second part where the data extraction process is, it had an amalgamation after we had the source code. It had an amalgamation of several medical terminologies. Old CPT4s and new CPT4s. And a thing that we noticed is that there were codes that we didn't know anything about. What are these codes? They aren't CPT, they aren't SNOMED, nothing. So it turned out, went back to the hospital, it was internal hospital codes. And that explains the type of data received. So these challenges and solutions, it went through a cycle which triggered the following cycle that you see here. First one, we had to educate hospitals on the OHDSI mission, request data, and then inspect that data related to the ETL requirements for the OHDSI, not just data and that's it. And then we would identify missing information, and then we would move on to the second phase, which I love that phase. It's comfortable here. We leveraged the use of OHDSI tools. I would say thank you Usagi and developers of Usagi, because due to the fact that we had a lot of internal hospital codes, just last week we have finished about 30,000 internal hospital codes using Usagi. So after that, we White Rabbit, where we understood the terminology, Rabbit in a Hat, and leveraged the use of Usagi. We have generated an ETL blueprint. Upon successful loading to the CDM, we will hopefully, at the end of this process and coming on to the next hospital, we hope for a smoother process, one that we are both us from the team from the SFDA and the hospitals know what is required from each part and work out to bring the best out of the OHDSI community. And thank you so much for this. And the OHDSI community could be the best collaborative community out there, actually. So thank you so much.
Thank you so much, Fatima. How amazing is that? I am incredibly impressed by your hard work. So as we continue our journey, we're going to shift gears a little bit here to another talk. We have Dr. Leonardo Mendez-Bu, who is a specialist in preventative medicine. He's going to tell us a little bit about what's going on in Spain, especially as it relates to their journey in the information system. Welcome.
Well, hello, good afternoon. So thank you, the organization, for inviting us to present our experience in this journey to mapping our data to the common international model. I'll begin by presenting our team, because every effort is a team effort. So I have here with me Talita Duarte, also from Barcelona. In these people you see here, there are Maria del Mar and Talita are more research-oriented. Eduardo Mosilla is a statistician. He's into shiny art, all those things. And I'm a doctor with a tendency to database hacking and all that thing. So as you will see, if I start so you can understand better who we are and where we come from. In 2010, my institution is a health provider. It's the main health provider for primary care in Catalonia, and it also manages 8 of the biggest hospitals in Catalonia. Made an alliance with the research organization that is SIDIAP Jordi Gol in order to develop a platform. We don't know how to call that exactly. It's a database, it's a platform, it's a system that it aimed to develop the research based on the electronic database, electronic health records that were the main source of information at that point in time. So as the health provider, we had the knowledge of the database. We previously, to starting this journey, already provided a research database. And in this instance, we were trying to do the internationalization of the structure in order to carry out studies in more reproducible ways. So our health provider is it's composed of, in primary care, 287 primary care practices, which each one has approximately 10,000 patients, and the 8 biggest hospitals with 4,000 beds and approximately 50% of the activity, of the hospital activity. And also in the left, you can see a lot of other different care units, mostly from primary care setting, but that are not exactly that the primary care as we know it. There are teams to treat pregnant women, to take care of the end-of-life stage, mental institutions, well, a lot of different type of cares we have. So what we have as an asset is that we have a very good representation of Catalan population. We are situated in the northeastern of Spain, and in this map you see the basic health areas, that's called, where we have practices. And this is, in the left you see in the right you see the distribution according to the age, the cohort, the calendar year of the cohort. You see a big axe when the civil war started around 36 to 39. So what kind of data is available? We have data from general data, like I assume most of us have, the age, date of birth, gender. Also about the proper health service, who's his physician, who's his nurse, the type of, if it's an active person, is a pensionist, and all kind of clinical data, drugs dispensed, but also drugs that going into the reimbursement system, vaccinations, conditions in several vocabularies, parameters that we already were using for clinical studies, labs, referrals, sick leaves, hospital discharge, well, many kinds of data. So when we approach this task, this journey to map, Peter visited us in Barcelona. He introduced us to the tools. The White Rabbit is very useful for characterizing your database. So we aimed at our existing database, which is in a MariaDB database. And it provides the Excel that Erica showed in her presentation. This Excel can be fed into the next tool, Rabbit in a Hat. It provides the user interface to do the mapping, the mapping of columns and tables, and also to put design the ETL in a logical sense. But it also have another tool that you can feed the codes and their description, and it tries to map it to approximately language processing to a suggested code. We did this for the codes that are not international, that are local codes, but also for international codes like ICD-10, that is the Catalan version. There are extensions by our institution, and so we got mappers to review all that. So it provides us with a relation with the source code and a standard code. So we had, before we started with this database that we characterized, when we started, I didn't have a specific hardware to put it on. So I was sharing platforms. I was very uneasy on breaking things for the production system we already had in place. And since we know we need to put it somewhere else, I started to work in a containerized system, so I could redeploy it when we had the good hardware. So I took this database, a version of the database, put it in a Docker Compose file that puts it up in a Docker engine. Next thing we found is that not all databases are supported. It's very difficult for OHDSI to support every possible database. But we have experiences in Maria database. So we, again, using containers, this is provided for us by Docker Hub. And there are places where you can download those things and just run it and deploy a Postgre database. So it will hold the transformed data. And also, I found a beautiful gem in OHDSI repository that is BroadC. BroadC already has the tools containerized, so you can download it and run it. And it puts the main tools. It puts Atlas, all its infrastructure, and it puts the methods in a RStudio software deployer. Then we learned that we needed to put other kind of databases, not only the CDM. For example, We learned that the Atlas requires its own database just to support the tool. It's the Web API scheme. But also, if you want to update your database and don't destroy results, you need a result database. And the last one is the Scratch database. That's very useful because when we started to run analysis, it took too long because they weren't parallelized. And when you run the parallelization, it can make use of another database that calls Scratch to speed the analysis. And the way we got data from the Maria database to the Postgre database is to creating a stage database to hold the transform data. We did this with the SQL language ETL with a client, put that ETL in the middle and run it, and got the domains that we got mapped in the OMOP scheme. And then we tried several ways to move the data from the Maria database to the Postgre, some tools, and in the end, the one that worked the fastest was to export it as CSV files and copy that into the database. So this is in summary the whole picture of the process. And as a result, we calculate we have more than 24,000 terms mapped to the standard codes. That's representing 1,400 million registers. These are the domains that we have worked on. The first ones that put the CSV icon, are the ones we have already passed to the Postgre database and can be used in the Atlas tool. And this is the kind of reports that Atlas shows, and it allows us to compare it to the things we were seeing earlier than introducing this scheme. For instance, 7 million people with continuous observation periods. The age of starting is a big peak in the 0 years because people being born from 2006 up until now is already captured, and the rest are people that got into our system being of older age. When we see at this graph, it was very happy for us to see that we have a lot of people follow for a lot of years. We have like half our population follow for 10 years or more. The distribution of cohort year is the same we saw earlier with this characteristic war axe here. Then we could characterize, for example, the dead people. The dead people were coming from two different sources. We have the administrative death, and in the little one is the people that dies in the hospital. Also, we're running, well, the characteristics that male have higher mortality than female, that's as expected. And since you can run Achilles analysis, it shows you things you didn't see before. For example, I have medical discharges with the death status that were later coming into an administrative database. And all those kind of things, you iteratively can see what happens and make corrections or explain it at least. So it's very important, the things that we're saying this morning about not just building an ETL for one time, because it's for sure that you will be reusing it, and the model changes, the vocabulary changes, and the database changes, but also your decisions about how do you treat the data gets better. So just to finish, in the conditions, we saw that it had the same frequency ranking that we observed previous to this migration. Since we have many primary care people, we have common cold, low back pain, those kind of things. And the things we can conclude is that OHDSI tools are very successfully implemented in SIDIAP. The thing we would like to do another way than knowing now what we know is that perhaps it's better to build the tools prior to ETL. You know, the Atlas requires the database already in the OMOP system, but maybe it's better to do the tools deployment before, even with sample data, so you can do this iteration quicker. We also have to assess the quality of the other domains. We haven't done the quality, like drugs and measurements, and do a replication of a scientific study. And since we use this Docker deployment strategy, we think that many people could benefit from this kind of deployment strategy that you can just run and redeploy many times as you need. Thank you.
Thank you, Leonardo. You sounded a little bit like an audio compression track that gets, sped up because I pushed you off the stage. But that was wonderful work that you're doing in Spain. It's very exciting to see the continuing of the evolution. And we're going to go even further forward into the method side of things. Nicolas Turin is part of an institute in Bordeaux. He's in Bordeaux Pharmacoepi. He is a scientific officer, and he's going to talk about evaluating the OHDSI methods as it relates to drug-related outcomes. Welcome, Nicolas.
Well, thank you. So, as my colleague said, we're going to speak about empirical assessment of case-based methods for the identification of drug-related outcome in the SNDS, the French National Healthcare Database. All the results that I will show you are based on the Al Capone project. It's a project funded by the Ministry of Health, and it has been designed, conducted, and analyzed by our platform in Bordeaux under the supervision of a fantastic scientific committee that I would like to thank. A bit of background. So we all know here that risk identification performances drastically depends on the method you use and also on the settings you use. But something that we can forget, but not here, I guess, is that the environment is also very important. The database matter. So we need to assess and to test the tools that we are going to use in the database in real life to ensure the generation of a meaningful point estimate. You need to know the background noise of your database if you want to be able to interpret it correctly, the point estimate that you generate. In France, we have a wonderful database, le Système National des Données de Santé. It covers 66.6 million persons, so almost the overall French population. It's very powerful. And inside, we have individual pseudonymized information on drug dispensing, deaths, hospital discharge diagnosis, cost, procedures, and a lot of other very interesting variables. We cannot access directly to the full database, but we can ask for database extraction that are available for public health purposes after the approval by the Data Protection Agency and the National Health Data Institute. The objective of our work was to evaluate and compare the performances of three case-based methods in our database: the self-controlled case series, the case control, and the case population. The case population, it's kind of a case control, but the difference is that you use aggregated data of the overall population instead of control. It's very useful when you don't have any case and control to match and to adjust for different variables. And so we want to use this case-based method for the identification of 4 health outcomes of interest: acute liver injury, acute kidney injury, myocardial infarction, and upper gastrointestinal bleeding. How do we do that? So we basically, or not so basically, we try to reproduce the OMOP experiment for the one who know that. So we adapt the OMOP reference sets that we merge with the EU RADIA reference sets. And so at the end, we get 4 health outcomes of interest with a set of positive and negative controls for each one of the 4 health outcomes of interest. We restricted the pairs to the one with a minimal detectable relative risk below 1.30 to ensure that when we are looking for an association, we have enough power to find it. And we applied that to the 4 database extraction that we requested, so one for each health outcome of interest. So at the end, we get 4 sub-databases, with the corresponding reference set and the population extraction. Then we try to detect our drug outcome pairs via with our three case-based design, but we try different settings for each one of the designs. So for example, we change the adjustment method. We try to adjust for seasonality. We try to adjust for age, for use of other drugs. We change the number of control match per cases. We change the risk window size. So at the end, we get 96 variants of self-control case series, 20 of case control, and 80 of case population. And each one of these variants was applied to all the drug outcome pairs. So at the end, we generated 26,068 point estimates. So that's a lot of analysis to run. And we use this point estimate to assess the discriminant ability of each variant method, calculating the area under the ROC curve to try to approximate the accuracy of the variants, also calculating the mean square error and the coverage probability. So what did we get? So in this wonderful table on the left side, you have the size of the extraction. As you can see, for myocardial infarction, on 6 years, we get around 300,000 patients. And that was a big issue because in France, because of the law, we are not allowed to put the data out of the accredited structure. So we are not able to use Amazon Web Services, for example, to compute all our analysis. So to be able to run that in-house, our 26,000 analysis, we had to resample the population extraction. It's the right part of the table. As you can see, when we decrease power, we decrease the number of potential detectable controls, but I think that we get enough control to run all our analysis. And this is the main result. So again, you have your 4 health outcome of interest, and inside you have the best design variants for each case-based design. So we have the best SCCS for UGIB with the best CP and the best CC. On the right side, you have all the detail about the method we use with all the setting applied. So the main point is that, as expected, the self-controlled case series achieved the better performances with the area under the ROC curve most of the time over 0.8 till 0.94 for acute liver injury, with very accurate measures. As you can see, the mean square error, it's almost 0 for some variants, 0.07 for UGIB, for example. On the other hand, the case population we test was not very efficient. The mean square error is huge compared to the self-controlled case series one, with most of the time extreme value for the sensitivity and the specificity. So based on that, we can say that it's not a very good method for OLED generation, but it's still very useful because, in fact, what we get is the real rate of an event in the population, which is not the case with the self-controlled case series because you get relative incidence. So that's an example of what we get with the best SCCS self-controlled case series variant for myocardial infarction. So on the left side, you have the negative controls. On the right side, you have the positive one. So as expected, so we were very happy to find that most of our negative control are negative, but we get some surprises. There are not really surprises because we can explain them. For example, for sucral fat, that's a drug you take when you have digestive pain, when you have cirrhosis, but cirrhosis can be confounded with referred coronary pain. That will be the prodrome of a myocardial infarction. So sucral fat here, it's a typical protopathic bias. We can try to interpret also amoxicillin with enzymatic inhibitors. So you take an antibiotic when you have infection. When you have infection, you have fever. When you have fever, your heart rate increase, so your risk of doing a myocardial infarction also increase. So that's totally consistent. You have also other example with sulfate ferreux. I don't know how to say that in English. On the right side, you have the positive controls, so most of them are positive. We were also very happy. You can see kind of a lack of power for some example, but that will be explained because we are dealing with a resample size, a resample extraction. So we try to replicate that in the full population with the best and the most accurate designs. In conclusion, we were able to implement the OHDSI methods library in the SNDS. So just to know, we haven't yet fully mapped all the SNDS to the OMOP common data model. We are working on it, but it's huge. There is a lot of very specific code, as we have seen in the first presentation. So we are working on it. But we are able to map the most interesting table for this kind of study. We have a first overview of the case population performances. As I told before, it's not very useful for all generation, but it's very useful for having an idea of what the rate of an event in the population respect to the people exposed to a drug or not. The self-controlled case series achieved the best performances across all outcomes with a high discriminative ability and a high predictive accuracy. And that helped us to define reference methods and setting for the identification of drug-related outcome in our database. So the idea now is to apply this gold standards method for routine alert generation. And we imagine something like running all the references method every year to be able to detect new drug-related events for new marketed drugs every year. And all of that thanks to the OHDSI community. Thank you.
Thank you, Niklas. That's some amazing work you guys are doing. Just goes to show the power of a little bit of persistence and doing things in tandem. It sounds like a very agile process. Well, our last speaker, I heard a rumor, has published or is in the process of publishing 26 papers in the first quarter of this year. So, you know, we've left the good stuff for last. So Dr. Ismay Gogner is a professor in the Center of Surgical Science in Denmark, and he's going to talk to us about the future of personalized surgery. And like I said, I heard he's figured out the dissemination piece, so I am all ears. Welcome, Doctor.
Thank you. Thank you very much for the honor of the podium. It's a very, very big honor. I think last time I was this nervous was in a conference of only anesthesiologists. So, as a colorectal surgeon, I don't feel comfortable right now, but I hope that you will be looking past that. This work is a tremendous work by a very, very great team that I'm representing. Janis Strakas as our data scientist and group leader, and our friends from Odysseus. So thanks for the work. I will be flying into the topic, presenting the clinical story. We have this use case of colorectal cancer, which is a disease increasing tremendously within the next 12 to 14 years, doubling in incidence and mortality. Our problem for our patients is that they are elderly and they are increasingly comorbid. So we need to find out how to adapt our surgery and our perioperative care in order to meet these challenges. The problem is also, of course, that these patients also represent a high degree of comorbidity. And the more comorbid these patients are, the higher risk of mortality within 1 year. So how does our surgery affect our patients on the short term? And if it's oncological surgery, how do we get into the subject of how to improve their short-term outcomes in order to increase long-term outcomes? But on the other hand, it doesn't help us if we help the patient that we operate them and they die of the surgery because we want to cure their cancer. We have a department doing a lot of minimally invasive surgery, so we're doing laparoscopic and robot-assisted surgery. These are data from our center. State-of-the-art ERAS, so we are doing state-of-the-art perioperative care. Even if we do this is 600 patients, we still have 25% of our patients having complications and readmissions and increased length of stay. So how can we find these patients in the best way, and how can we integrate the personalized medicine with big data approach to find these patients in need of special care or stratified care? So we need to find this guy here. Okay, as I said, the trade-off is to try to create the best short-term outcome without sacrificing the long-term outcomes. I'll make an example. It's the same thing as when we're doing medical treatment. We need to give the best drug with the lowest toxicity and the highest clinical effect. So as surgeons, we are actually over-treating a lot of patients, and I'm really sorry for my patients that we are not actually better on stratifying these patients with their disease. When they have a tumor in their colon or in the rectum, These two groups, T1 and T2 tumors, these are just merely inside the muscular wall of the colon. We remove the whole colon or the whole hemicolon because we suspect that there will be diseases in the lymph nodes. But we are overtreating 90% of those who have T1 cancers. We are overtreating 80% of those who have T2 cancers. So we're exposing them for huge surgery or major surgery where we actually, if we were better at predicting it, their risk, we could just do an endoscopic extraction of the tumor and let the patient home after a few hours. So we need to integrate phenotypic data and we need to integrate deep mutational data, deep immunological phenotypic data in order to be improving our patients. So what we're creating in Denmark is a Patient Like Me platform where we'll find the patients in our colorectal cancer registries and in our OHDSI CDM who actually have been through the treatment that we are planning for this patient. Just a few words about the Danish health data scene. Every person in Denmark have their unique personal identifier. This has been going on since 1968. All the data are produced at any healthcare level and is digitally stored. We are going through the data through curation and quality control pipelines. And I, as a clinician and a researcher, have a full availability of these data, making quality improvements and fulfilling the data cycle. So these are some of the registries. There are hundreds of registries. All these registries are full national registries. Cancer patients, 99.9% of our patients are in these cancer registries. So these are deep phenotypic registries on all patients with these different cancers, or if there's, for example, drug statistics, diabetes, stroke, head and neck cancer, tissue, molecular biology, actually we also have on a national level. So the obvious advantage is that we have an extreme deep phenotype of these patients. Okay, so we started out doing this proof of concept CDM, where we take the first wave of CDM data sources, and we're concentrating on the data sources that we actually believe will be valuable in a predictive model where we will try to stratify patients to different kinds of treatments. So it represents, as you can see, almost 20,000 concepts, and we have in our OMOP model more than 75,000 patients with a very deep phenotyping and deep description. The way we've done it is to integrate it in our prediction model on these different levels. And the following slides are the important ones with respect of understanding how we will integrate this in our clinical setting. So for our patients, when we get them in the hospital with their cancer, we will take their patient data and put it into the relevant model. We will select our model, and we will create our risk prediction. So we have done this at this moment with the preliminary work. We are producing AUCs of 0.80. And this will be integrated as a tool that I can use in my multidisciplinary team, where I will have it as a decision-aiding tool. And I will then, together with my colleagues from oncology, radiology, and pathology, and hopefully anesthesiology and internal medicine, I will be able to stratify. Should I train my patients before surgery? This is one of the trials we're doing in my unit. 4 weeks of muscular training increases the oxygen uptake by 30%. It reduces their frailty dramatically. It really creates it's a really, really effective pill. So the elderly, frail patient needs to be 4 weeks prehabilitated. How should I operate? Depending on the patient's phenotypic risk. Should I do a big incision from what we usually call Copenhagen to Paris? Or should we do laparoscopic incisions with 4 small holes? Or should we just remove the tumor endoscopically? Should some of our patients have immunotherapy before surgery because they have a higher risk of getting a recurrence? Or should we not operate? I think this is one of the most interesting questions, is actually to select the patients that we're not going to operate. So for the course of the patient, we're integrating our tool with the module. This is the first priority of our tool, to integrate it preoperatively in our MDT. I will get back to this intraoperative phase. And we will put it also in our post-discharge plan to stratify which kind of patients will we do a more intensive follow-up and what kind of patients can we just let go without an intensive follow-up program. So our assistance right now, how we're going to build up our model is to try to integrate wearables in our data. So in addition to the patient data that we have by interviewing the patient and taking our blood samples, we will also integrate wearables preoperatively and wearables postoperatively in order to feed our common data model and use machine learning algorithms to find the patients before they develop their complications. And we are actually, within the last couple of months, also beginning to integrate a strategy regarding including data during surgery. So data from the anesthesia, processed data about how the surgery is going, how's the median blood pressure of the patient, how can we use the logistics during the surgery of how much time we use for the different phases of the surgery, and integrate this all in a common data platform where we, and excuse me for just going back to this slide, can put this model into 3 different phases where I believe as a clinician I would be having a stratified approach based on the prediction that we produce. And in Denmark at the moment, the teamwork that we're doing right now, we are actually trying to build up this software platform to integrate first in the preoperative phase and then secondarily in the intraoperative and postoperative phase. Thank you very much for your attention.
Thank you, Dr. Gogner. Who's impressed? Who's excited? Yeah? Well, why don't you all stand up on your journey? We are not going to have Q&A here. They're going to go down to their posters, and we're going to have time now for 45 minutes for another part of the collaborator showcase. So 45 minutes back in here for what I hear is going to be the best part of the day.